Okay, if we assume that the absolute value of x is less than 1, in other words, x is between -1 and 1, then for every real number k, we can write the binomial function 1 plus x raised to a power using this series called the binomial series. It would be 1 plus kx plus k times k minus 1 over 2 factorial times x squared, and so on. So the formula here, the nth term would be k times k minus 1 times k minus 2 times the quantity k minus the quantity n plus 1 all over n factorial times x to the n. Okay, now this is actually a power series, and we can actually use it to represent certain expressions that we may not have a way to represent as a series without this. So for instance, the cube root of 1 plus x can be written as 1 plus x to the 1/3. So using this power series representation with k equal 1/3, I can actually write the power series for this. So let me just show you. Just first of all, you start with 1, and then you have k times x, so that would be 1/3 times x, and then you have k, which is k would be 1/3, and then 1/3 minus 1 would be minus 2/3. So if you have 1/3 times minus 2/3, you would have minus 2 over 3 squared, right? 1/3 times minus 2/3 to give you minus 2 over 3 squared. And then you also have the 2 factorial down here. Okay, well, it is a little tricky, so let's do it again. If you have, you take k for the next term, you'd have k, which is 1/3, and then 1/3 minus 1 would be negative 2/3, and then 1/3 minus 2 would be negative 5/3. So you'd have 1/3 times negative 2/3 times negative 5/3, and since you have a negative times a negative, therefore we have a plus. So 1/3 times 2/3 times 5/3 would be the same as 1 times 2 times 5 over 3 times 3 times 3, which would be 3 cubed. And then, of course, you have to divide also by 3 factorial. Okay? And so basically, we're getting an alternating series where the numerator is just going to be 1 times 2 times 5 and so forth up to 3n minus 4. Now, let me just show you here how that fits each term here. First, let's look at the denominator, then I'll show you the numerator. So the denominator is pretty easy. You can see that this would be divided by 3 to the 0 times 0 factorial, that would be 1. And then this would be 3 to the first power times 1 factorial, that would be 3. And then 3 squared times 2 factorial for the second term, 3 cubed times 3 factorial for the third term, and so forth. So for n equal 3, I mean. Okay, so this would be 3 to the n times n factorial. That's going to be your denominator. Okay, so the numerator, you're going to multiply these numbers out till you get to 3n minus 4. So let me just show you that this would be the 0, n equals 0, n equal 1, n equal 2, n equal 3. So let me show you. We multiply 1 times 2, and then if n equals 3, we get 3 times 3 minus 4, and that gives me the 5. So that's kind of a weird puppy there, but that's the nth term. Now, this next one, I'll let you go ahead and sift through it, but it's basically the same thing. But instead of 1 plus x, I have 1 plus x to the 4th. So basically, you do the same thing, except everywhere there's an x up here, you actually would replace it with x to the 4th. So you would actually get, for x, you would get x to the 4th. For x squared, you would get x to the 4th squared, which is x to the 8th. For x cubed, you get x to the 4th cubed, which is x to the 12th, and so forth. Okay, now you could actually use this representation to approximate an integral for that function. Obviously there should be a dx right there, but you could integrate this function. Okay, so up here you'll notice I came up with these terms here. Okay, so I'm only going to use these first three terms to approximate. Actually, it's four terms, counting the one. Okay, so since we're integrating from 0 to 1, okay, when you integrate each of these terms, I didn't actually show you the integral here, but basically this would integrate to x, this would integrate to x to the 5th over 15, and this would integrate to 2x to the 9th over 9 times all of this, and then this would integrate x to the 13th times 10 over 13 times all of this. But anyway, again, if you integrate this and evaluate it from 0 to 0.3, just those four terms, you'll just have to evaluate it at 0.3, because if you evaluate it 0, all the terms will be 0. So all you have to do is evaluate this at 0.3, and then that should give you four values. It looks like this value here is probably so small I just left it off. So I really just used three terms. And so when I evaluated those three terms and combined them, I got 0.300162. So two questions remain. One question is, for what values of x can we normally expect a Taylor series to converge to its generating function? Okay, so in other words, the interval of convergence. And how accurately do a function's Taylor series polynomials approximate the function on a particular intervals? Well, that's where we need Taylor's theorem. And Taylor's theorem basically says this: if f and its first n derivatives, f prime, f double prime, and so forth, out to f to n derivative, are continuous on the closed interval from a to b, and the nth derivative is differentiable on a to b, then there exists a number c on AB such that f of c, I believe this should say f of c. Okay, so I was wrong. This is f of b here. Okay, so f of b would equal f of a plus f prime of a times b minus a, because you're evaluating it at x equal b, so therefore x would be replaced with b. And then the second derivative at a over 2 factorial times b minus a quantity squared. And then you're going out to the nth derivative of a over n factorial times b minus a to the n. And then the c comes in out here at the n plus 1th value. So plus f, the n plus 1th derivative evaluated at c, times b minus a to the n plus 1th power over n plus 1 factorial. And so that c, in other words, this term would actually make f of b equal this series. And this theorem actually leads to a formula called Taylor's formula for f of x. So if f has all the derivatives that are needed and in an open interval containing a, then for each positive integer n and for each x in the interval, f of x is equal to f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared plus so on, all the way out to the nth term over n factorial times x minus a over n plus r sub n of x. Now this r sub n of x is what takes up the slack. That's the remainder term, okay? And that remainder term is actually equal to the n plus 1th derivative evaluated at some number c times x minus a to the n plus 1 power over n plus 1 factorial. So where c is some number between a and x. So the first example here says show that the Taylor series generated by f of x to e to the x at x equals 0 converges to f of x for every real value of x. Now we showed earlier that e to the x actually is equal to this series, but now we know if we add the remainder theorem on there, it's got to equal that, and the remainder theorem would be the n plus 1th derivative evaluated at c over x minus a to the n plus 1 over n plus 1 factorial. Okay, now since the n plus 1th derivative at c, that would simply be just e evaluated at c, because the derivative e to the x is just e to the x. So that would be e evaluated at c times x to the n plus 1 over n plus 1 factorial for some c between 0 and x. And then since e to the x is an increasing function, we said for some c between 0 and x, well, if x is 0, e to the 0 would be 1, and if x is x, we would get e to the x. So e to the c must lie between 1 and e to the x. And now if the x value were a negative number, then the c value would have to be a negative number. And if the c value is a negative number, then e to the c would be some number less than 1. If x were equal to 0, then e to the x would equal 1. So basically you would have it trapped between 1 and 1. So therefore, the remainder would basically just be 0. And then the third case, if x is greater than 0, then c would be greater than 0. And so e to the x would have to be greater than e to the c. So if x is less than or equal to 0, then we go up here to this remainder term, then we know that e to the c would have to be less than or equal to 1. So therefore, I can just replace e to the c with 1 here, and therefore the remainder term must be less than or equal to 1 over n plus 1 factorial absolute value of x to the n plus 1. Now, but if x is greater than 0, okay, then we need to leave the e to the x in here with this, and the remainder would be less than or equal to the term as it's written up here with the x in there. Now the limit of this, the actual limit of this would actually be 0 for all x. So since the limit of this is 0 for all x, so the limit of the remainder term would be 0 as n approaches infinity, and therefore the series converges to e to the x for all x. So both of these actually go to 0, so the series converges for all values of x. Now honestly, some faculty will not even cover the information about the remainder, and so I'll just hold off the rest of this discussion in the next video, and if you are interested or you need to see some information about this remainder theorem, then you can go ahead and watch the next video. I also have another interesting identity here at the end about Euler's identity that you'll see on that next video. So we will shut this off right here with this example that we just completed, and I'll finish this on the next video.